Hello. Today I want to talk about another application of a binary tree. Uh, First, to motivate this, uh, when we send messages, the size of the message determines how much time it takes to send the message, given that everything else is given that other things are equal. So if you want to get the most out of your bandwidth of what you purchased, you would like to send messages in some way that would minimize the amount of bits you have to send. Normally, each character we send requires a string of 8 bits, where each bit is a 1 or a 0. Now, there are some places you might read where it's 7, but then they put on a parity bit and you get to the 8. So this is normal, let's say. Can we do better? That's the question. Well, English is not a language where all the letters appear equally. Some letters appear in messages more than others. The most frequent letter in English text is E, and Q is way down in the list. There are published lists of these frequencies. One of them is from Cornell, and I'll bring it up for you right now to show it to you. Well, I will if I can figure out. There it is. This is what Cornell has done by taking a lot of words, 40,000. Now, that may seem like a lot, but there are others that have taken even more. And what they've done is count the number of each of the letters. They use capitals. I think probably they meant either capital or lower. And then they've computed the frequency based on how many letters there were. And then for E, we divide the number of times we have E by the total number of letters and get a percentage, or at least the frequency, pardon me. Now, you'll notice that E appears much, much more frequently than Z or X. So one thing we might be able to try is maybe we could work out some way to have different numbers of bits represent different letters. We might try to represent E, for example, with fewer bits than Q. Since E is more frequent, we would be saving bits. Now, this is not a novel concept. In fact, there is a coding that we're going to look at in a minute that has already been done to do this. The method to do this is called Huffman coding. Now, I actually, there are variants of this. I may actually have it a little different from the way you might see it in a book, but basically it's the same spirit. The idea is the following. Create a tree, a binary tree, and put the frequent letters nearer the root. Then, so as an example, let's build a little tree here. I'll just have just a box there. I don't want anything special. And I'll bring in some pointers. So we'll have 2 pointers. It's a binary tree. So one will go here. And one will go there. And we could keep going. We could have a few over here. And maybe another one over here. And I'll put in one more. No, I won't. I'll leave it the way it is. And what we're going to do is we're going to say, if we go, oh, I didn't want that. Just not do that. If we go left, we're going to assume that that's a coding. In the coding, that will be a 0. And if we go right, the coding will be a 1. And the same thing will go everywhere else inside this whole thing. Now the tree can get big. We have 26 letters. And at the bottom of these, at the leaves, we're going to put the letters. So we might say, just get these over. We might say that this is A, and this is T, and perhaps this is E. This means we would use 0, 0 to represent A, 0, 1 to represent T, and just plain 1 to represent E. That's the idea, to create that tree. And the idea is to put the ones that are more frequent nearer the top so they take less letters. Well, now, how do you do this? And you can see it's an application of a binary tree. And the algorithm is reasonably simple. I've written it out, and I'm going to show it to you from here, from my C++. The algorithm depends on having a queue. In fact, I think I'll go back and write some things before I show you that. We create a queue. But the elements in the queue are stored in a funny way. They're in order. They're stored with, I think, the larger numbers. We create a queue. I better tell you what the elements are in the queue before I do anything else. Each element in the queue is a Huffman tree, a binary tree. The nodes of this tree, let's say the leaves of the tree first. The leaves of the tree are the frequencies. And I wanted to avoid having lots of real numbers. So what I did was I multiplied all the frequencies by 100 to get them all to be integers. Each node that is not a leaf has its the leaves of the tree, pardon me, have the frequencies as their value. Now, each node that is not a leaf has value equal to the sum of its two children's values. The idea is that each time we create a new node by putting two nodes we have together, we keep track of how frequent that subtree is. Now that's complicated, especially since how do we create a queue that contains trees? We've never done that before. Furthermore, how much work are we going to have to do to keep this queue in order? That seems like a big task. So the queue needs to be in order by the values, with the largest first. Well, this seems like a tall order. However, as usual, data structures helps us take care of it. The C++ has a set of built-in data structures. They're in something called the STL. I think that stands for Standard Library, something like that. Now, there is a structure that is more than a queue, but is a queue. The structure priority queue is a queue that automatically keeps the items in order by whatever we want. It's not as easy as it looks because it's not a simple thing. It's what's called a template. In other words, there are many, many types of these. You can decide what goes in the queue, and you can decide how to order the queue. And that way, that gives you many choices, but you have to know how to put those choices in. This is maybe the second example of you've seen of a template. If you look at one of my older projects, you'll see I had a template in one case. Now, what does this look like? Let's go back and let's see what this looks like. First, you need queue and utility. I'm not sure you need both. I know you need queue, and for something I was doing, I put in utility, but I may have gotten rid of what I used for the utility. I am creating a special structure. This is a tree. I call it my tree. And my tree has a value and a letter, which for some mysterious reason I just put down as a question mark. And it has 2 children because this is a binary tree. So it has a left child and a right child. And they are pointers, and I start them out as null. I initialize the tree by giving it the value I want to put into V and the letter I want to put into let. And I also have a generic constructor because otherwise the machine complains. Now, that is a tree. It looks like one node, but it depends on how many, what the left child and right child are. We're going to build those up one by one and make them bigger and bigger. So I have my tree. I want to be able to print the tree. So I just wrote a print routine. It's not awfully different from the kinds of print routines you've seen. What it does is basically post order. It pre-order. It prints what's in the root, then prints the left subtree, then prints the right subtree. And those levels that you see there are just to make it so that it indents more. Now, here's the tough part. You got to define the operators, less than and greater than. You don't have to define much about them. You just have to say, use the less than that comes with integers, because the values are integers and I want to order them by the values. But you have to have an operator. That's a requirement. And you have to have the both types. So I have greater than and less than. Now comes the priority queue. And this is where you're going to start seeing that it takes a little more work than you think. A priority queue gets 3 items. First, it's whatever goes into the priority. We have to tell you what goes in there. It's usually a pair of things. The first item you put is what you want to order by. I want to order by my trees. And the ordering on my trees depends on the val. The second item is a vector of trees. That's what I'm going to have there. I'm not even sure I use it, but I put it in there just in case. Then I have over here the less. That says use the less than operator that I've defined. And I have to spell it out. Less, for vector of my tree is the value type X. If you'll notice up here, less than has a tree and a second tree, a first and a second tree. But this is the way you have to do it. This is what I mean by it's not trivial. I had to look that up, and frankly, there are not many places on the web where they do a good job of explaining it. They all show it, and there's different ways they show it, but very few show an example. Now, I want to print it. So all I do is print, and I've got it there. Now, let's see. I create a priority queue. I'm going to call the priority queue X. And then I have an in file. In that in file, all I've done, the wrong in file, here it is. I put in the letters and the frequencies. They happen to be in order, but that just was there. It was easy to copy it from the other setup, from the web. What I do is I read all the items one by one. I create a my tree with the frequency and the value of the letter, and I put it into X. Now, automatically, X takes care of keeping that queue in order. I don't have to. I don't have to do all the rearrangements that are necessary to make sure I get it in the right place. That's all done by the queue, which I love. Means I don't have to work as hard, though you don't have to work as hard when we do that. So now I have the queue set up. And here's the argument. Here's the way it's done. Answer is going to be the final result. While it's not empty, I'm going to create a new tree. It's the top of the queue. So I'm going to take the top of the queue. I'm going to take its letter, its value, and its left subtree. Pardon me. Its name, x.toptree. That's a tree. Then I pop it. Then I do the same again for the second item in the queue. And now the trick is that, as you see over here, when we were doing this before, let me write here. If I had A and T as separate entries in the actual queue, I would take out T, I would take out A, and what I'm doing is creating a new node. This node here, which has no name, but will have a value. And its left and right children will point to the trees with A and T in them. To avoid, I had to do something. I had to put some kind of letter in there. So what I did is question mark. That means it's not really a letter. And I used that when I was printing things out. Now, I push it in. I take the new tree, and I essentially replace the first two that were in there by that new one. So I push it in. If it's empty, though, I'm done. Answer is just the tree. And it has to be star MT because MT was put together as a pointer to the tree. And I just keep doing that as long as I want. And when I get it empty, everything works out. So this printed out the tree, and then I went from there. Now, this case I actually did with all of the 26 letters. So I'll run it for you. And there it is. That's the tree. It's not beautiful, but at least I managed to wipe it out in one fell swoop. What you're seeing here, well, one of these days I'll keep it on the screen. All right. What I'm trying to show here, I started out with all the letters as they came in. Then at the very top, the root of the final tree is just a node, and its frequency is 9999. That's the total of all of them. Then that val has a right child here, and then a left child that's lined up under it there. And then this left child, pardon me, has a left child here and a right child there, and so on and so on. So it creates the tree from the top down, and each indentation indicates that we have children of the node that above it that we've indented from. Now I took this tree and I put it in a file. So I put it over in an Excel file. That's not it. That's not it. This is it. That's not it. I was right the second time. This is it. This is quite a task. First, those are the things I copied in. There's a better set of them down below so you can read them. Then over here, I actually created what the tree looked like. I just managed to get it on one page. Although right now it doesn't want to be on one page. But I was able to get it on one page at one point. It's a really complicated looking tree. But it's easy to read if you know what you're doing. For example, it says that if you want to represent an E, you go from the root 1, then a 0, then a 0. So 1, 0, 0 represents E. T is the next most frequent number. So to get to T, you go 1, 1, 1. So if I want to represent T, I only send 3 bits, rather than 8. And the same thing for E. Now, if I want to represent D, it takes me 5 digits, and all of them are 0. I go 0, 0, 0, 0, 0. This tree could be looked at as a decoding tree or an encoding tree, whichever way you want to look at it. It would say, if I got a message that started off as 011, then I would know that about 011, I would know I'm over in this section here, and then depending on whether I get a 0 or a 1 next, I have either an S or an R. So that when you get the message, you take it to the tree and just travel down until you get to a leaf. And then that is the letter that represents. On the other hand, if you want to encode a message, you might find it easier to use this form. You just might say, well, if I'm going to put a D in, I have to write 0, 0, 0, 0, 0. If I'm going to put an A in, I have to write 0, 0, 0, 1. And then I just throw them all together. I don't leave spaces between them. So, for example, if I were going to encode A, T, T, then the result is. Now, A is represented by 0001. So 0001. T is represented by 111. So after those, I type 111, 111. And that'd be what I would send. And the same thing works backwards. If you got that message that you see as the result, you would go to the tree and you'd start 0001, and that would put you at a leave, and you would have a letter. Then you'd start over again from the top to get the next letter, and so on and so on. It's rather ingenious, and it does save a lot. For example, this is a 3-letter message. Normally it would take 24 bits to send. It took 10. In other words, it cut out 16 bits. Pardon me, 14 bits. And that's more than half. Now, it's not going to be that perfect in all cases. I took very frequent letters. But it is a saving. It does make it easier in the sense that you don't use as much of the bandwidth as you would have, and therefore you can send more in the same amount of time. Now I'm going to give you a homework on this. This will go out on the web very shortly, and it's basically to do what I just did. I'll give you that file, and you use the Huffman tree to encode the following message. That means put it in bits. When I did an encoding for that second part, what I did was I looked at the, not at the tree, but at the list of all the way it came out from the computer to get the letters I needed. Part 2 is to go in the other direction, to the decoding. Part 3 is to see how much you saved. So I want you to look at the message in part 2. You don't know at this moment how many characters it is. You won't know until you decode it. But whatever number of characters it is, multiply by 8. That's the number of bits that a normal transmission would take. Then count up the bits that this takes and see how many you saved. And if the number of saved bits divided by the total you would have had to send, that's, well, I think I have to multiply by 100, but that's the percentage of the normal length that you saved. So that's where we are. I'll be putting out this, the video, and these files that I was working with here. I'll include the C++ file also. So there are two things to take from this. The Huffman tree is an example of a binary tree, but I'm also looking at a priority queue that is automatically given to us by C++. And I want you to notice, in this area here, I didn't worry about pointers. I didn't worry about any kind of having to sort things. That was all done for me. That's the idea of data structures. If you can once you get the data structure written, you can think in terms of the problem and not have to get into the nitty-gritty details of how to implement it. So that's it. I'll be talking to you again soon. Bye now.